The assignment, you should find the assignment just under modules, and then it just should be final review. It should be just listed as final review. So that's what we're going through. We're going through the final review today. We'll start with question 1 and just see how far we can get today, and then we'll finish it all on Wednesday. The final exam will open on Wednesday, just after class. We'll open on Wednesday, and we'll go through Monday. So Wednesday through Monday. Wednesday, December 4th through Monday, December 9th, just over in the testing center. And something new I'm going to be doing with, based off of how the midterm went, I am going to kind of give the testing center instructions to collect your scratch work. So make sure to show your work as you're going through. They have the scratch paper that they give you with the different boxes. Make sure to just keep nice, organized scratch work, because you'll turn that in, and I will use that as I grade it just to give you partial credit if possible. Everybody okay with that? So just make sure you're showing your work as you take the test. Okay. And that applies to all of my online students as well. Okay, so let's go through this. Start with number 1, and we'll just go through as many as we possibly can here. So, number 1, going all the way back to chapter 1 when we first learned about limits. So my first one is the limit as x approaches 1 of x squared plus 3x minus 4 over x squared minus 1. Well, when we work with limits like this, what's a good thing I can always start doing? By doing? What's something I can always do to start?
Factor off the bottom.
Yeah, there's probably going to be some factoring here, but even before we start factoring, it's always a good idea to go ahead and plug this value in, see what happens, right? Plug in 1, see what happens. If I'm working with a continuous function, then the limit is just going to be whatever the function value is. Let's plug it in, see what we get. Let's see, we get 1 squared plus 3 times 1, which is just 1, minus 4. So 1 plus 3 minus 4 is equal to 0. I get 0 on top, and 1 squared minus 1, well, that's just 0 as well. I get 0 over 0, which, of course, we know as indeterminate. If I get an indeterminate form, that tells me, okay, I gotta manipulate this. I gotta mess with this somehow in order for me to get a more meaningful result. 0 over 0, I can't just put that in as my answer. So, what do we notice about these two functions? Well, sure enough, yeah, I can factor the top and I can factor the bottom. Okay, so if I do that, what does the bottom factor to? X squared minus 1? That's a difference of squares, so I get x plus 1 times x minus 1. Awesome. Top. We have x squared plus 3x minus 4. So I need two numbers that will multiply to equal negative 4, right? Multiply to equal negative 4 and add to equal positive 3. Positive 4, negative 1, right? Oh, is that what you said? Positive 4 and negative 1. Very nice. So x plus 4 and x minus 1. What do we notice? We notice that I now have a factor of x minus 1 both on the top and the bottom, and those factors are going to cancel. And now I'm just left with this limit as x approaches 1 of x plus 4 over x minus 1, or x plus 1, sorry. What have I done? I was able to eliminate the discontinuity. Now I don't have an x minus 1 in the denominator anymore, and I can go ahead and plug in 1 for x. And I get plug in 1 for x, and I get 5 over 2. Okay. Which I guess is equal to 2.5, but you don't have to go that far. Awesome. Okay, questions about number 1? Good, nice, simple limit problem to get us started. Okay. Okay. Number 2. Number 2 is talking about the difference quotient. So it gives me a function. By the way, you'll notice that your problems are all going to be very similar, just different numbers, right? So just be aware of that. That I'm just pulling from my problems that I had, and they're going to be different numbers than you, but it's the same concept. It's the same idea. So it gives me a function, negative 3x squared minus 2x minus 2. Your equation is going to look a little bit different. And what does it want us to do? It wants us to use the difference quotient. Evaluate this as part of the difference quotient and simplify as much as we can. So we got to remember what the difference quotient is. What's my difference quotient? DQ. Difference quotient is f of x plus h minus f of x over h. So that's my difference quotient. Notice what I don't have attached to this. I don't have the limit part of it, because usually we take the limit as h approaches 0. Well, that's what we do if we want to calculate a derivative, right? We let the difference quotient, we let h approach 0 for my difference quotient in order to calculate a derivative. But this one's not talking about derivative. It's just putting it in the difference quotient and just stopping there. So there's my difference quotient. So that's what I'm going to do. I'm gonna put this equation. I'm going to put this equation into my difference quotient. Okay. So what does f of x plus h mean? Right. Anywhere I see an x, I'm instead going to replace that with x plus h. Use parentheses to help you out here. Okay. So this gives me. Here, I'll do it this way. F of x plus h is -3, but instead of x, I'm going to put x plus h, so all of that squared, minus 2, but instead of x, I'm going to have x plus h. Notice how I use parentheses because this negative right here is going to affect both the x and the h. Okay, sorry, I'll keep going. Minus 2. So that's f of x plus h. What's f of x? Yeah, it's just your starting equation. So it's the same thing as your starting equation. So from here, I'm ready to go ahead and plug all this in. So my difference quotient here equals -3 times x plus h squared minus 2 times x plus h minus 2. So that whole piece minus my f of x, which is just my original function. All over h. Everybody okay with that? Right? This is your f of x plus h, and this is your f of x. And then there's your minus. Okay? And so from here, it does ask you to simplify as much as possible. So this is where I'll start multiplying some things out, right? I gotta multiply this part out. Sorry, I'll use a highlighter for that. I gotta multiply that piece out. I've got to distribute over here. I've got to distribute this negative to all of these terms. That negative is going to distribute to each of these terms. So what is this going to end up looking like? I'm going to end up with -3x squared minus 6xh minus 3h squared minus 2x minus 2h minus 2 plus 3x squared plus 2x plus 2 all over h. Any questions about any piece of this? Okay. These all became positive because I distributed this negative, and negative times negative equals a positive, so that's why all of these are positive. Where does 6xh come from? Well, when I multiply this out, I get x squared plus 2xh, and the 2xh times the -3 gives me negative 6xh. Well, think back to when we learned about difference quotients. What do we hope to happen? What should happen here as I simplify? Some things cancel. Specifically, what should cancel? Anything that doesn't have an h in it. Anything that doesn't have an h in should cancel. So let's look. I've got 3x squared, or -3x squared, and positive 3x squared. So those two terms cancel. I have 6xh has an h in it, so that's probably not going to cancel. But then I have -2x and positive 2x. And then -2 and positive 2. So sure enough, everything that didn't have an h term in it canceled out. And that leaves me with -6xh minus 3h squared minus 2h all over h. Since every term in the numerator contains an h, what can I do? I can factor out an h. And I'm left with -6x minus 3h minus 2 all over h. These h's cancel, and I'm done. Now, real quick, if we relate that to derivatives, right? What did we say about derivatives? Derivatives, I just let h approach 0. Now that I've simplified it, if I let h approach 0, that term goes to 0, and I'm left with just negative 6x minus 2. Well, guess what the derivative of that equation is? Negative 6x minus 2, right? So that's how the difference quotient relates to derivatives. Awesome. You're going to notice my handwriting get bigger and bigger as we go through this. I don't know, it's just a weird phenomenon with this program. Okay, question 3. Awesome. This one, question 3 is just, I give you this equation, y equals x squared minus 2x plus 5, or something similar, right? And it's just good practice, and then I ask you to find the derivative. What does this derivative require? Quotient rule. So this is just good quotient rule practice, where you look at your top function and your bottom function. Quotient rule is you keep your bottom function multiplied by the derivative of the top, which is 2x minus 2, minus the top function multiplied by the derivative of the bottom, which is just 2x. All over the bottom squared. Okay. And then, of course, you can simplify that. But remember, with these Pearson assignments, sometimes it's better to just put it in unsimplified so you don't worry about missing points on your simplification. So that's all number 3 is. It's just good quotient rule practice. Okay. Question 4. It gives you an equation, y equals 2x to the 6th minus 10x cubed plus 7x, and then asks you to find this. What is this talking about? Yeah, it just means the 5th order derivative. I'm going to take the derivative 5 times with this equation. Okay. Well, remember, think back to how derivatives work. I can take the derivative of each piece individually, right? I can just worry about each term and take the derivatives of them separately when I take the derivatives of my function in general. So if I look at the term 7x, what happens when I take the derivative of that? It becomes 7. When I take the derivative again, it becomes 0. If I take the derivative again, it stays 0 from there on out. Once it gets to 0, it's just going to stay at 0. So if I take the 5th order derivative, what's going to happen to this term? It's just going to go to 0. What about this term?
Goes to 0 too.
Yeah, it's also going to end up going to 0 because it's the power of 3, right? I have negative 10x cubed, but if I take the derivative 5 times, right? If I just think about this derivative, I get negative 30x squared, take it again, I get negative 60x, take it again, I get negative 60, take it again, I end up at 0. And how many derivatives did that take me? 4 derivatives. It took me 4 derivatives to get 0. So this term is also going to go to 0. The only term that's going to stay, the only term that's not going to go to 0 over 5 derivatives is this first term. So if I think about that term, that's my term. That's my first term. First derivative? 12x to the 5th. Second derivative? 60x to the 4th. Third derivative? 240, sorry. I should just look at my numbers because I've got all these numbers. 240, x to the 3rd. Fourth derivative, 240 times 3. 720, yep. 720x squared. And remember, at this point, all your other terms have gone, right? By the fourth derivative, the other term, both of the other terms are at 0. Okay. Fifth derivative, 1440x. Okay. So sure enough, my final answer is just 1440x. Now, if all this other stuff didn't quite make sense to you, that's totally fine. You can go ahead and just take the derivative like normal, right? Y prime is 12x to the 5th minus 30x squared plus 7. But you'll notice as we keep going, those other terms are just going to go to 0. Okay. So, right, if you just take your derivative straight, you're going to end up with the same thing. Okay. Cool. Any questions about this one? Awesome. Okay. Question number 5. So, oh man, I gotta pick up the pace here. Okay. Yeah, this one's sketching your graph. So this one's all about sketching a graph, and it gives me some basic information here. So first of all, it tells me that f prime of -3 is equal to 0. What does that tell me about -3? Just that piece of information. Yeah, the graph flattens out at -3, right? Because the derivative is 0. The graph flattens out at -3, meaning -3 is a critical point. Okay? Well, it also tells me that f double prime at -3 is less than 0. What does that tell me?
It's going down.
It's concave down, right? It means I'm concave down. Well, if my graph is flattening out and it has a downwards curvature, what does that tell me? Local max. So right there, I can already make a decision about -3. I know -3 is a local max, or at least -3 is an x value. So there is a local max at -3. Okay. It keeps going though, and it does tell me that f of -3 is equal to 1. That tells me where the local max is. So -3, it has a y value of 1. So I have a y value at 1 at my local max. Okay, so I know I have a local max at -3. Let's keep going. Next, it tells me that f prime of 1 is equal to 0. So 1 is also a critical point. 1 is also possibly a local min or a local max. F double prime of 1 is greater than 0. What does that tell me? Local min, right, because that tells me it's concave up. If I have upwards curvature, then it's a local min. Right? If I know I have a critical point, if it's flattening out, but it also has upwards curvature, I know I'm working with a local min. And then it tells me that it also tells me that f of 1 is equal to -5. So that tells me what the x value is, or the y value is there. Now I can honestly stop here. It also tells me about like where the inflection points are. I think that's the other thing it'll tell you about. It'll tell you about where the inflection points are. But I honestly don't need to know. I can already pick the correct graph just based off of this. So what we're looking for is a graph that has a local maximum at -3 and a local minimum at -1. Or sorry, at +1. I've got a local minimum at +1 and a local maximum at -3. So that's what we're looking for. Everybody okay with that? Okay. Moving on. So next we get into, I think there's 4 straight problems all about optimization. Can you guess what type of problems you might see on the final exam? It's probably going to be at least one optimization problem on there. Okay. So number 6 gives me this situation, and I think it provides the picture for you. Okay. And it defines some variables for you, which is nice. You guys don't have to define the variables, it defines them for you. And it says we want to maximize this area. Maximize this area enclosed by not just one of them, but all of them. Okay, so we're doing the area of all three of these. Everybody okay with that? We're not just maximizing one of these. We're maximizing the whole area. Maximizing this whole area. Okay. Why is this optimization? Because optimization, we're optimizing the amount of area that we can fit in here, which really boils down to maximizing or minimizing. Okay. And then it also tells me that we have 976 yards of fencing. And then I want to maximize the area. Okay. So what is this right here? What is this right here? That's my constraint. Okay. That's my constraint. That's going to help me optimize this here. Okay. But what can I start out by doing? What can I start by doing? Write an equation, right? If I want to optimize area, I need an equation for area, right? So I need an equation for area. Area is equal to, use the variables that it gives you. My area of this total shape will just be x times y. Length times width. Length is defined as x, y is defined, or width is defined as y. So there's my area. My problem is two different variables. I've got two different variables involved here, so I have to get this all in terms of one variable. Okay. How do I do that?
976 yards is equal
Yeah.
to 2x.
My yards of fencing. I use my constraint. I'm constrained by the amount of fencing that I actually have. So I need to now come up with another equation, but this time I need to come up with an equation for my constraint. I need an equation for this. Okay. What's that equation look like? 976 is equal to, right? Since it's a total amount of fencing, I'm going to set that equal to how I would actually calculate my fencing. How many x values do I need? 2 x values, right? For the top length and the bottom length. And then plus, how many y values do I need? 4. I need one right here, one right here, one right here, and one right here. Oh, hello. Cool. So, there's my constraint equation. What can I do with that constraint equation? Solve for one of the variables. Doesn't matter which one, but I can solve for either one of the variables. I'm going to solve for x because the coefficient's smaller. So I'll subtract 4y onto both sides. Minus 4y. That gives me 976 minus 4y equals 2x. Then I'll divide everything by 2. And I get x is equal to 976 divided by 2 is 488 minus 2y. Okay. Very nice. So I use my constraint equation to get one variable in terms of the other. What do I do with that?
Multiply by
Yeah, now I can come back here to my original area equation, but instead of having x times y, I now know what x is equal to. Right? I know what x is equal to. So that gives me 488 minus 2y times y. Are we okay with that? Since x is equal to 488 minus 2y, I can plug that in for x. Now I can simplify, distribute this y, and I get 488y minus 2y squared. Perfect. We were able to get my area equation completely in terms of one variable, in this case y, or the width. Now what?
set it equal to 0.
Not yet. We don't want to set it equal to 0 yet. First, I need to take the derivative, right? Because we want to look for critical points. We want to look for where the graph flattens out or where the derivative is equal to 0. So I'm going to take the derivative, then set it equal to 0. So the derivative here is just 488 minus 4y. Okay, notice how, because this is just in terms of one variable, I know it's y, but I'm not using implicit differentiation. I'm just treating y like my independent variable and taking the derivative like we normally do. So no implicit differentiation here, just take the derivative like normal. And like we said, now I can set this equal to 0 and see what I get. Okay, I'll add 4y on both sides. And I get 488 equals 4y. Divide by 4. And I'm left with y is equal to 122, I believe. Yep. 122 yards. Perfect. So now I know this distance. This distance is 122 yards. How do I figure out x? Plug that in to this equation right here. So I get 488 minus 2 times 122 is a y value, so I'll plug that in for y, and that'll let me solve for x. So 48 minus 244 equals x, so that gives me 244 equals my x. So this distance was 244 yards. Perfect. Okay. This is a great example, kind of a more simple example of just how that optimization process works. Write your equation for the value you want to optimize. If it's not in terms of one variable, use your constraints to get it in terms of one variable, then take the derivative, set it equal to 0, and solve. Notice I only have the one critical point, so I can go ahead and assume that that's my maximum value. That's going to give me my maximum. Questions? Okay. Online students, if you guys ever have any questions, feel free to email me. And also feel free to pause this video whenever you want. Okay. Number 7. This is another optimization, but this one's, you're going to notice, is a little bit different. Okay. This one's all in terms of finance. So we're working with a suit company that produces suits, and it gives you a cost equation for producing X number of suits. So 3,500 plus 0.5x squared. That's your cost of producing X number of suits. So X is the number of suits. And then it also gives you a ooh. Does anybody have it up? Does it give you the profit equation? What does it actually give you on this one? Number 7?
I didn't see like
Yeah, I
an
couldn't
assignment
find
for
it.
the final review.
What? Was anybody able to find the final review assignment?
I'm there.
Oh, you're there. Okay. So it's posted. That's weird. Here, let me see if I can find it real quick. So just we'll pause this programming real quick to make sure we can all see it. So if you go to Canvas, let's see, Canvas, let me go ahead and view as student so you can see what you guys are seeing. And this is right. By the way, I will post this video. This is the one from last semester, so I'll replace this with the one from this with you guys. And then if we go to My Lab Math Assignments, and scroll all the way down, review for the final exam right there. So I'm not sure if I go to assignments, can I see it there? Maybe that's what's the problem. Yeah, that's probably the issue, is it's not showing up in just, it's not showing up under the assignments tab, but if you go to modules and access it through there, you should be able to see it. I'll see if I can figure out why it's not showing up on assignments. Okay. So anyway, I guess since I pulled it up, I can look at this problem. So question number 7, let me just get some clarification here. Oh, yeah, gotcha. Okay. Back to what we were doing. Okay, so it gives you a cost equation, and then it also gives you a demand equation. Oh, no, I need to make sure and use my numbers so that I don't mix up my numbers. So it also gives you a demand equation, right? How do demand equations work? Demand equations relate price with quantity, right? If you raise the price, you're going to be able to produce less, or you're not going to be able to sell as many. If you want to sell more, you need to lower the price. Okay. So, part A. This one has multiple parts to it, and so this one's a great review of how all of this revenue, costs, profit, all that kind of stuff works. So part A is find your revenue equation. What's your revenue equation?
Your price equation times X, because you have to do price times quantity.
Yeah, price times quantity, right? That's your most basic revenue equation, and since it doesn't give us anything other than that, it doesn't give us anything else that's calculated towards revenue. My revenue is just price times quantity. How many can I sell at what price? So this is just P times X, which is 150 minus 0.75X times X, which if I simplify that, that gives me 150X minus 0.75X squared. Everybody okay with that? There's my revenue. Okay. Part B. What's my profit? And yeah, profit, like we've talked about before, is just revenue minus cost. So I'm going to take my revenue equation and subtract my cost equation. So I get 150x minus 0.75x squared minus 3,500 plus 0.5x squared. If I simplify that, I get 150x minus, let's see, I need to distribute this minus to both of these terms. If I have negative 0.75x squared minus 0.5x squared, I get negative 1.25x squared minus 3,500. Okay? Everybody okay with that? There's my profit. Part C. How many suits must the company produce and sell in order to maximize profit? So does this count as an optimization problem? Absolutely, because I'm maximizing profit. That counts as optimizing. I'm optimizing profit or maximizing profit. So this absolutely counts as an optimization problem. So if I want to maximize profit, what do I need? I need an equation for profit. If I want to be able to maximize it, I need an equation to actually work with. Do I have an equation for profit? Check, yes. I already have it. So I already have an equation for profit. So part of my work is already done for me. I guess we did the work, so it wasn't done for me. It's just we're already done with it, right? We've already done this piece of it. We've already come up with a profit equation. Okay. Notice, what do you notice about this equation? It's already in terms of one variable. So I don't have to do that extra work of getting this into terms of one variable. Like we had to do with the last problem, right? The last problem, when I first wrote my equation, it was in terms of two different variables, length and width, x times y. and I had to do some work to get it all in terms of one variable. But in this case, my profit equation is all in terms of x, which means, can I go ahead and take a derivative? Absolutely. So because it's only in terms of one variable, I can go ahead and take the derivative of this. Once again, why am I taking a derivative? We want to find critical points, right? We want to see where the derivative is equal to 0. We're looking for critical points. And my derivative, 150 minus 2.5x. What do I do with this derivative? Set it equal to 0. And solve. So I get 150. Well, here, I'll walk through it. I add 2.5x to both sides. And I'm left with 150 equals 2.5x. Divide by 2.5. And I'm left with x equals 60. Once again, since I'm only getting one critical point, I don't have to test whether this is going to be a minimum or a maximum. I can go ahead and just assume this is a maximum. So, how many suits do they need to sell to maximize their profit? 60 suits. They need to sell 60 suits. I don't know if that's like per month or per year, or I don't know. So 60 suits. Part D. What is that profit? No? Yeah. No. Aha. Wait. No. Let's see. What is the maximum profit? Yeah. What is that maximum profit? How do I figure that out? Just plug it into your profit equation. Really, I'm just finding out what's P of 60. So 150 times 60 minus 1.25 times 60 squared minus 3,500. And you should end up with, at least in my case, you just throw all that into a calculator, and I got 1,000. Okay. Ooh, and then part E. Part E is just asking, okay, so what price should you put your suit at? What should the price be? What equation do I use for that? Yeah, I have an equation for the price. That's what this one is. That's my demand equation. So I can just use that and plug in 60 for x. Okay. So I get, give me the actual. So I get P is equal to 150 minus 0.75, and I know what my x value is. My x value is 60. Plug that in, and I get $105. So I should sell them at $105 to maximize my profit at $1,000. Cool. Questions on this one? So still technically optimization, because I still did that process of took my derivative, set it equal to 0 to find the critical points. But with this one, it was already all in terms of one variable. All the prep work was done in part A and B. Part A and B took care of all the prep work so that by the time we got to part C, where they asked us to maximize the profit, it was as simple as just taking the derivative and setting it equal to 0. Now, that is not the case for these next couple. Question number 8. I think we did this one in class, didn't we? The university and the football tickets. All right, we did this one in class. So you've seen this one before. This is just reminding ourselves how this one worked. So let's see. What information does it give us? First of all, it gives me that at a price of $28 per ticket, attendance averages 40,000 people. Okay, you'll notice I'm making a table to help me organize this. Okay, every decrease, I need to be looking at, oh my goodness. Okay, I'm doing this again where I'm looking, I need to turn this I need to ignore this thing and just look at my numbers. Forgive me, I'm going to change the numbers so that I don't have to do all the math. When the price was $16, we averaged 40,000 people attending. Okay? So it gives you that first. Last year, they charged $16 and they had an average of 40,000 people attend. But then it'll tell you that every decrease of, in my case, it was every decrease of $2. So if I decrease it by $2, adds an additional 10,000 people. So if I decrease it to $14, I should see 50,000 people show up. If I decrease it to $12, I should see 60,000 people show up. If I decrease it to $10, I should see 70,000. So on and so forth. Everybody okay with that? Okay. Then it tells me that every person at the game spends an average of $5 on concessions. So $5 concessions per person. Okay. And now I want to maximize the revenue. Maximize revenue. Okay. Do you remember how we set up the revenue equation? Once again, you guys have seen this before. It's just been a while. How did we set up that revenue equation? There's two parts to it. What were those two parts? We had the revenue from the actual sales, ticket sales. We had revenue from ticket sales and revenue from concessions. Well, what does revenue from concessions look like? Yeah, it's just 5 times X. Or A. We'll stick with X, where X represents attendance. Okay. Okay, so there's my concessions revenue. What about ticket sales? How do you calculate ticket sales revenue? This piece is going to look very similar to how revenue looked like in the last equation, or in the last problem. How do we normally calculate revenue? Price times quantity. So it's just my price times my quantity. Remember, X represents quantity, P represents price. And then my revenue is just those two things added together. Okay. Of course, I'm running into that problem where my revenue equation involves 2 different variables. So I have to get one of these in terms of the other. Okay? I have to get one of these in terms of the other. How am I going to do that? That's what this table is for. That's what this table is going to help me. Notice, if I look at what's happening with this table, what kind of relationship's going on here? A linear relationship, which means I should be able to create a linear equation out of this, right? I should be able to create a linear equation here. So what's my slope? It is negative. Negative 10,000. I lose 10,000 attendance every $2. Yeah. So I'm losing 10,000 in attendance every $2 that I increase the price. You could move this around. In fact, it probably makes more sense to put the negative down here. I gain 10,000 attendance every time I decrease the price by $2. But when I simplify this, what does it give me? It just gives me negative 5,000. So it doesn't matter where you put the negative. Your slope's going to be negative no matter what. Okay. So there's my slope, negative 5,000. Okay. So that gives me X, or A, is equal to negative 5,000 P, right? I'm going to lose 5,000 for every dollar I increase the price. That's what that negative 5,000 means. Plus, how do I find that y-intercept? How do I find the y-intercept? Yeah.
Plug in like
Base.
16 for P.
Sure.
and the differences.
Right. So there's a couple of different ways I could do this. First of all, I could just, since I don't know what it is, just put B there, right? Remember, we use B for the y-intercept. So I could just put B there, and then like Pace said, I could go ahead and just plug in one of my points. Pick one of my points. Sure, I can pick 16 and 40,000 and plug that in. So I'm going to plug 40,000 in for X and 16 in for P. And when I do that, negative 5,000 times 16 is, oh goodness, negative 80,000. Right? Yep. Add 80,000 to both sides, and you get B is equal to 120,000. Very nice. How else could you have done it? You could use point slope form. I could also just keep using the table. Just keep going down on your table. Make a really big table that goes all the way to 0. And that'll also get your y-intercept. But regardless, there's my linear equation. So based off of this information, I now have this linear equation that X is equal to negative 5,000 P plus 120,000. What do I do with that? Plug that in wherever I see an X. Okay. So that gives me this revenue equation. P revenue is equal to P times negative 5,000 P plus 120,000 plus 5 times negative 5,000 P plus 120,000. Simplify that a little bit, and you get negative 5,000 P squared plus 95,000 P plus 600,000. Okay. Where's the 600,000 coming from? That's 5 times 120,000. That's 5 times 120,000. That's where the 600,000 comes from. Where's 95,000 coming from? Well, that's P times, that's 120,000 P plus negative 25,000 P. So that's combining your inner terms. Okay. Whew. We are past the hard part, because from here, what do we do? We got the revenue equation all in terms of one variable. From here, optimize it, right? Take the derivative, set it equal to 0. So I get negative 10,000 P plus 95,000. Set that equal to 0. Solve for P, so I'll add 10,000 P on both sides. Divide by 10,000. And I'm left with 9.5. Awesome. That's the price I should set it at, $9.50. Questions? Questions? Yeah. Hey.
Can you go back to, so I know like the P negative 5,000 or negative 50,000. Can you go how you got to the bottom step? So
Yeah. So that's probably just my simplifying, right?
Yeah.
So I can multiply this P through to both terms,
Okay.
and I get negative 5,000 P squared plus 120,000 P, right?
Yeah.
And then over here, I'm also going to distribute this 5 to both terms, and that gives me plus 5 times 5,000 is negative 25,000 P plus 600,000.
Okay.
So there's the 600,000. 600,000 just goes right there. But when I combine these two like terms, sorry, that's like blinding to your eyes. But 120,000p minus 25,000p gives me the 95,000.
And then so like on my problem, for instance, it's every decrease of $4 adds 10,000 people. And what was yours again?
Every decrease of $2 adds 10,000.
Oh.
So for you, all that would change is instead of 10,000 over -2, it'd be 10,000 over. What do you, in order to get those 10,000 more people, what would you have to decrease the price by?
$4.
Right. So yours is just going to be 10,000 over 4 instead of 10,000 over
-4.
-4.
2,500.
Right.
And I did positive 2,500.
Oh yeah.
So,
Yeah, it needs to be -2.
Okay.
Okay. Awesome. Okay. Number 9. Now, number 9 is another optimization problem, another example of an optimization problem. And I will go ahead and tell you right now, I feel okay with myself. I'm going to sleep well tonight. Telling you guys that you're not going to see number 9 on the test. Okay, this problem is about, number 9 is about the sporting goods store with the pool tables, storing pool tables. And it's a fun problem. It's a fun problem-solving problem, but it's more intense than I expect you to be able to do on the test. So you're not going to see it on the test. Yes.
So don't study number 9.
Don't spend a lot of time studying number 9. You still have to do it if you want to get 100% on your review, but you're not going to see number 9 on the test. Okay. So I'm going to go ahead and skip this one. But if you, I guess, I'd like to give you just like a little bit of help on it, but it's, if I crack that shell open, I don't know how long we'll be here working on just this one problem. So if when you're working on this one and you're like, how the heck do I do this? Please feel free to reach out or come into office hours tomorrow and I can kind of go over this one with you. It's fun, but a little bit more complex than what I expect you to do on the test. So, everybody okay if I skip this one? Okay. So, I'll just put, ask if you want help on this one. It's not on the test. Okay. Number 10. Now remember, the test is like 21 questions long. The review's 28. So there's definitely going to be problems on the review that you're not going to see on the test. But the whole idea is just we're reviewing all these different concepts that we learned throughout the year. Okay, number 10. So number 10 was the problem about the item that the price and the demand also depend on time. So it gives me a price demand equation as follows. Okay, where P represents price, X represents quantity, okay, or number of sales, right? But both of these, both the price and the quantity, depend on time. Okay, so I can say price is a function of time and quantity is a function of time. They're both functions, they both depend on time. So find the rate at which X is changing when X equals 4, P equals, I guess mine, I gotta look at my numbers. Find the rate of change for X when X is 3, P equals 6, and dP over dt is 1.3. So this is what it's giving me. It's giving me X is equal to 3, P is equal to 6, and dP over dt is equal to 1.3. What is this talking about? What is dP over t? It's the rate at which the price is changing in regards of time. So it's a rate of change for price in regards to time. Remember, because we're assuming that X and P both depend on time. So if this question's asking, find the rate at which x is changing, what are we talking about? In terms of time. We're trying to find dx over dt. So what does that mean I'm going to do to this whole equation right here? I'm going to take the derivative all in terms of time. I'm going to take the derivative in terms of time. So let's look at the first piece. I can look at each of these pieces individually. So first piece, what's the derivative of 5p? Well, 5's a constant, so I can just, I can ignore that constant when I'm taking derivatives, right? It's constant multiple property. So I can ignore that constant of 5 and just look at p. What's the derivative of p? I'm taking the derivative in terms of time. So, right, what's the derivative of p? Well, I just get dp over dt, right? It's my derivative of p in terms of time. And like we said, I can just keep that 5 there. So when I take the derivative of that first term, I get 5 times p prime, or dp over dt. Okay, and we'll worry about plugging things in a little bit. Okay, what about the next term? What's the derivative of 5x? 5 normally, but what are we assuming about x? We're assuming that x is a function of time, and we're taking the derivative in terms of time. In fact, to help us out, remember, we're taking the derivative of all of this in terms of time. So what am I left with? I'm left with 5 dx over dt. Everybody okay with that? Ooh, this term. How do I take the derivative of that? Product rule, right. This requires product rule. Why? Because, once again, I keep standing up, but anyway. Once again, p and x, we're assuming they're both functions. They're both functions in terms of time. So if they're both functions, how do I take the derivative of two functions multiplied together? I use product rule. So I have to use the product rule right here. Okay? And I can pair the 3 with either one of my functions, but I can go ahead and say, let's say, I'm going to let my f function equal, I don't want to mix it up with up here. Oh, man. No, I gotta keep it. Okay, my first function is 3p. My second function is just x. What are my derivatives of each of those? This gives me 3 dp over dt. Remember, since this is all implicit differentiation, my derivatives are these rates of change here. My derivatives don't just go to 1, they go to these dp over dt's and dx over t's because we're taking the derivative in terms of t. So now I'll use the product rule here. So I get plus these two terms multiplied together. So 3p times dx over dt plus these two terms multiplied together. So 3x dp over dt. Awesome. So that's after I use the product rule. So this was my derivative of that third term. Equal, what's the derivative of 99? 0. Because even though we're taking the derivative in terms of time, 99 is constant. It's not changing in terms of time at all. So the derivative is 0. Okay. Now we solve for dx over dt. Right. Now we solve for dx over dt. And I could do it one of 2 ways. I could solve for it now and then plug in my values, or I could plug in my values now and then solve. But it's the same work involved. So let's go ahead and plug in my values now. Do I know what dp over dt is? I sure do. Okay. This is 1.3. Plus 5, do I know what dx over dt is? Not yet, that's what we're solving for. plus, do I know what P is? Absolutely, P is 6. dx over dt, I also, once again, I don't know what that is, so I'm going to leave that. Plus 3, do I know what x is? Yep, x is 3. dp over dt is 1.3. And that's set equal to 0. Okay. After I plug all this in, let's see, I have 6.5 plus 5 dx over dt plus 18 dx over dt plus 11.7, still equal to 0. Combine like terms, I get 23 dx over dt, and then I'll subtract both of my constants over to the other side and combine them, and I get negative 18.2, divide by 23, and I'm left with negative 0.79. It does say round to the nearest hundredth on this problem. Okay. Negative 0.79 what? What's my unit for this? What? What is x? What did x represent again?
Sales after.
Yeah, sales, right? I mean, I think I mentioned quantity up there, but it's the quantity of products you're producing or selling. So it's, and so if we're talking about, I think, yeah. So in our case, it's sales, x over t. What's t? Time. And in this case, days. Okay. So this is sales per day. I'm losing about almost a full sale per day. So remember, your unit for any derivative or any rate is going to be this idea, this thing of like this per this. Your unit for any derivative is going to be a rate. Okay, let's see. Questions about this one? Okay. Let's look at number 11. Number 11. So this is, number 11 is dealing with like the differentials idea that we talked about. So it gives me this S of P equation, 0.07 P cubed plus 3P squared plus 6P plus 14, which represents, it's a supply function for a certain product. SP is the number of items produced, and price is the P dollars. So how many products are you going to produce if you set the price to a certain amount? So price is my independent variable. The supply, how many you will actually produce, is your dependent variable. Okay. We work with demand equations a lot, but this is my supply equation, which we did talk about in supplier demand and, or sorry, what was it? Surplus. Producer surplus and consumer surplus, right? We talked about these supply equations. So then it says, use S prime of P to estimate how many more units a producer will supply when the price changes from $15 per unit. Well, I'm mixing up my numbers again. Use the derivative to estimate the change in your supply when P changes from $18 to $18.10. So the price is going to change from $18 to $18.10. And I'm going to use the derivative to estimate how that will affect my supply. Well, what does that mean I'm going to have to do? What's a great way to start this? Take the derivative, right? If I'm using the derivative to help me out, I should probably take the derivative. Nope. Okay, what's my derivative? 0.21 P squared plus 6P plus 6. Here's my derivative. And where the derivative is helping us out, so this goes back to this idea of differentials, which was back in, what was this, 2.7? Where my other way of writing a derivative, if you remember, is this Leibniz notation, ds over dp. It's how your supply is changing as p changes. Well, using that, remember, I can rewrite it like this. I can find my change in supply by using the derivative times the change in price. ds represents your change in supply. dp represents your change in price. Okay. So all I need to figure out is what do I plug in for P, and what do I plug in for dP? Let's start with dP. What is dP equal to? What's my change in price? Yeah, dP I just get, oh, sorry, I don't know why I drew it like that. dP I just get from up here. dP is your change in price, which is 10 cents. Everybody okay with that? So that's my dP. What do I plug in for P? 18, your starting amount. Very nice. So I'm gonna plug in my starting amount for P. So I'm gonna do S prime of 18 times 0.10. And just as a reminder, I want to use my starting amount. Okay. So then I get, let's see, 0.21 times 18 squared plus 6 times 18 plus 6. So there's my derivative with 18 plugged in times 0.1. And for my problem, I end up with 18.204. And this one I think is multiple choice, so all you have to do is just take that answer and match it to which of the options match that. Oh, and I put dollar signs. What? There's dollar signs next to this? I think this is a typo on the problem. There should not be dollar signs next to it. This doesn't represent money. What does it represent? This is how much the supply will change. How many more units will be produced if you increase the price by 10 cents? Okay. Cool. Questions on this one? Awesome. Question number 12. This will probably be the last one, and then we'll finish the rest tomorrow. This is a nice, simple differentiation problem. Okay, we've done so many applied problems. Let's take a break by just doing a nice, simple, take the derivative problem of natural log of x to the 5th minus 4 over x. And I want to take the derivative. So differentiate. Ideas? What is this derivative going to require? Chain rule. This is definitely going to require chain rule. But is there anything else we can do? I can use some of my log properties. Right. Anytime you see multiplication or division inside of your natural logarithm, in this case, what do I see? Division. Because I have division inside my natural logarithm, I can actually use log properties to make this a lot simpler. So this is actually just equal to what? Natural log of x to the 5th minus 4 minus natural log of x. I still have to use chain rule, but that's a much simpler equation to work with. Okay? Can I use any more natural log properties? No. I can't use any more because if we look at this piece, because there's subtraction inside your natural logarithm, that kind of ruins any chance of using more log properties. If there's addition or subtraction, if there's addition or subtraction inside of your logarithm, there's no properties you can use. Okay. So that means I do have to use chain rule for that piece. Okay. So let's start with that one. Let's start with that first piece. What is my derivative of natural log of x to the 5th minus 4? This is a good review of chain rule. Okay. So I could introduce a dummy variable u, right? I could. But with chain rule, we don't have to. That's something we consistently do when we're using antiderivatives, right? When we're integrating. But with derivatives, we got away with not actually using that dummy variable u. How does chain rule work again?
Take the first one, take the derivative of like the outside one.
Right, take the derivative of the outside function. What's the derivative of natural log?
1 over x.
1 over. So I get 1 over x if it were natural log of x. So in fact, what's the derivative of natural log of x? We just said that. That's just 1 over x. So that takes care of my second piece, right? But as for this piece, I don't just have natural log of x. I have natural log of this inside function. So what goes into my denominator? The inside function, right. I keep the inside function there. Okay? So since it was natural log of x to the 5th minus 4, my derivative is 1 over whatever's inside that natural log. 1 over x to the 5th minus 4. Everybody okay with that? But now what?
Then multiply by the inside.
Multiply by the
H of x. But it's not
the derivative of the inside function. So we don't just multiply by the inside function, we multiply by the derivative of the inside function. Okay? In our case, what's the derivative of my inside function?
5x to the
5x to the 4th. So just as a reminder, right, this piece right here represents the derivative of my outside function with the inside function still plugged in. And then this piece right here represents the derivative of the inside function. And that's what chain rule is. Okay. Where, originally it was just f of g of x, a function inside of another function. Everybody okay with that? Is that helping us remember how to do chain rule? And then like we said with this other one, it's nice and simple because I know the derivative of the natural log of x is just 1 over x. And that's as complicated as that one gets. Simplify this a little bit, and we're done. Okay, so we got through question 12, which means we have a lot more problems to get through on Wednesday, but those optimization problems took some time, and so I'm hoping these next few ones won't take us quite as much time. Aiden, yeah.
When's the exam due?
The exam opens Wednesday and it closes on Monday. So you have all the way through Monday evening to take the exam. So, yeah.
Will, for the hurricane testing center, just give them the scratch paper?
Yeah, I will coordinate with the Hurricane Testing Center of how they'll get that scratch paper to me. They might just fax it or something, photocopy it. But I'll coordinate with them. Make sure I can get your scratch paper. Thanks for the reminder.
No.
Cool. Okay, we'll continue this on Wednesday.